All right, in this section, we're going to see a couple of very powerful identities for cosine that are at the heart of many other identities that we're going to see down the road for cosine and for sine as well. So let me ask a general question here. If you have cosine of 2 theta, so cosine of 2 times an angle, can we say that that's 2 times cosine of the angle? In other words, can we factor a coefficient of theta out of the trig function? Now the answer is a resounding no. We are not allowed to do that. Okay, in other words, in a specific example, so an illustration of this, for example, would be, we know that cosine of 90 degrees is 0. Okay, but we could also write this as cosine of 2 times 45 degrees. Still 0, right? Because 2 times 45 is 90. But if we were allowed to extract that 2, kind of factor it out, then this would technically be equal to 2 times cosine of 45 degrees. But we know cosine of 45 degrees is rad 2 over 2. So that means this whole thing would come out to rad 2. But of course, on this side we have 0. 0 is not equal to rad 2. So this entire thing breaks down, and this would be the part where it breaks down. That's just not true. In fact, in general, it's not true that if you have cosine of some algebra like a plus b, you generally cannot just say, well, that's cosine of the first thing plus cosine of the second. It's just not going to be true. However, there will be plenty of times where we do have this particular situation and we need to deal with it. We need to do something predictable and manageable with it. And in particular, when we have cosine of a double angle, that's just a case where we have theta plus theta here. So again, we do need to find a way to deal with this. So that is what we will be doing in this section. We're going to come up with a particular identity for managing cosine of the sum of 2 angles. Okay, so let's motivate this particular identity using a circle. Now this is going to be a particularly interesting proof. We're going to go through this once, and then we're never going to need to go through it again because we'll have the pot of gold at the end of this. All right. So let's suppose we have a unit circle here, which means we're going to call this point 1, 0. Tell us that's the unit circle. And let's suppose we have some angle A. Let's put it in the second quadrant. So there's our angle A. Now, this is going to get a little clunky unless we start to assign some letters. So what we're going to do is we're going to say Q is cosine of A, and R is sine of A. And we're going to say that because this is a unit circle, that the coordinates here, of course, are cosine of A, which is Q, and sine of A, which is R. Okay, now let's get another angle, and we'll call it angle B. And let's put that in the first quadrant, say right here. And we will call these coordinates ST. And we will see that S, of course, being cosine of B, and T is sine of B. All right, so far so good. Well, now what we're going to do is we're going to take the angle A and we're going to subtract from it the angle B. So we get the angle A minus B. And we're going to label these points right here using U and V. So U will be cosine of the angle A minus B, and V will be sine of the angle A minus B. All right. Yeah, so this is how you clutter up a unit circle diagram. Well, we're going to make a key observation here. We're going to note that the distance between this point and this point is equal to the distance between this point and this point. And you can see that by imagining this particular triangle, which seems kind of balanced at the origin, and if you sort of just applied a little wind to it, it would go thump and fall over to the right. And so obviously the two red line lengths are going to be equal because they're corresponding parts of congruent triangles. So, okay, that means that if we actually calculate the distance of each of them, we're going to get that those two lengths are equal to each other. Now, since these two lengths are equal, that means that the square of their two lengths is equal, right? And it's actually going to be a lot easier to work with their squares, because the way we're going to work out these two lengths is using the distance formula from algebra, which we know has a square root, right? So we can avoid that if we just square everything. So we're going to do that. So that means that this particular length right here, which is given by the difference in the x value squared, so we're going to say 1 minus u squared, plus the difference in the y value squared, so that'll be 0 minus v squared. That's going to equal the square of this length, which is the difference in the x value squared, so s minus q squared, plus the difference in the y value squared, so t minus r squared. Okay, now what we're after is an identity involving u in terms of these other variables, so that we have this sum difference identity for cosine. So all we have to do is kind of isolate u in this identity and then write everything back in terms of sines and cosines, and we'll have our brand new identity. So of course we're going to need to do a lot of foiling. So on the left here we have 1 minus 2u plus u squared, which is what we get foiling out 1 minus u quantity squared. Here we have negative v squared, which is negative v times negative v, so that's actually positive v squared. And here we're going to have s squared minus 2sq plus q squared. And here, foiling this, we get t squared minus 2rt plus r squared. All right, so this is a mess, but wonderful things are going to happen. Because notice that we have u squared plus v squared. Because going back to our legend here, we have a few identities for free. Since q is cosine of a and r is sine of a, that means that q squared plus r squared is equal to 1. Right? Cosine squared plus sine squared is equal to 1. Similarly, we have s squared plus t squared is equal to 1. And that even applies here. It doesn't matter what the angle is. Cosine squared of a dump truck plus sine squared of the same dump truck is going to give you 1. So here we have u squared plus v squared is equal to 1. Which means that in our giant identity that we're working with, if we encounter any one of these expressions, we can replace them with 1. And good news, those are all over the place here. Because look at this. We have u squared plus v squared. So that is 1. We have s squared plus t squared. And we have q squared plus r squared, which is 1. So what does this really mean? Well, on the left, we have 1 plus 1, which is 2. So we have 2 minus 2u. And on the right, we have s squared plus t squared, which is 1. Q squared plus r squared, which is 1. They add up to 2. And then what have we not accounted for yet? Minus 2sq minus 2rt. Okay, so this is starting to look a little cleaner. We can do a lot better than this. We can also subtract 2 from both sides, completely eliminating that 2. So we get negative 2u is equal to negative 2sq minus 2rt. Let's also divide everything by -2. So what are we going to get? We're going to get u equals, this term here is just q times s, and the other term is rt, and it's being added because the negatives all canceled away. So this is our identity we just discovered. Well, it's not very meaningful in that form, but let's go back to writing it in terms of cosines and sines by consulting our legend. So u is cosine of a minus b. And q is cosine of a. S is cosine of b. R is sine of a. And t is sine of b. And this is considered the difference identity for cosine. So cosine of one angle minus another is equal to cosine of the first angle times cosine of the second angle plus sine of the first angle times sine of the second angle. Okay, so good news is we do not ever need to go that deeply into a proof for an identity again. We're going to be able to deduce all the other identities we need just from this particular one right here. So before we go and do any examples, let's quickly discover an identity for cosine of a plus b. Well, we don't have to go into all that analysis, like I just said. We can use the fact that we know the one for cosine of a minus b. So cosine of a plus b is cosine of a minus negative b, which means if we just use the identity we just discovered, but with b replaced by negative b, we're going to get a new identity for cosine of a plus b. So this is going to be cosine of the first angle, cosine of the second angle, plus sine of the first angle, sine of the second angle. All right, but recall that cosine of negative stuff is equal to cosine of positive stuff, because cosine's an even function, right? This is the negative angle identity for cosine. And similarly for sine, we have sine of negative an angle is not quite sine of the positive angle, it's actually negative sine of the positive angle. So that negative is going to come all the way to the front of this term. And we're going to get cosine of A times cosine of B minus sine of A sine of B. And that's the sum identity for cosine. Okay, so let's summarize these two identities. We'll put them next to each other so we can see how related they actually are. So we have cosine of A plus B, which we just figured out right above. That's cosine of A, cosine of B minus sine of A, sine of B. And cosine of A minus B is pretty much the same thing, but with a plus there. Okay. I often personally refer to these identities as the cosine, cosine, sine, sine identities. All right. Makes it easy to remember if you just chant that. Cosine, cosine, sine, sine. It's always first angle, second angle, first angle, second angle in all cases here. So cosine, cosine, sine, sine. First angle, second angle, first angle, second angle. And the plus or minus that's in the middle is always the opposite of whatever the operator was within the original cosine function. So here was a plus, so it's a minus out here. Here it was a minus, so it's a plus out there. All right. So for the rest of this lecture, we're just going to be seeing examples where we need to use this identity. All right, a great application of those identities we just uncovered is that we have now a wider range of angles for which we could evaluate the cosine function. So, like, what is cosine of 15 degrees? Well, 15 degrees is not one of our special angles, right? It's not 30 degrees, 45, or 60 degrees, or an angle with those as a reference angle, right? So this is new territory. And the way we approach this is by rewriting 15 as the sum or the difference of two angles with which we are familiar. So for instance, we could say 15 degrees is 60 degrees minus 45 degrees, right? That's true. Or we could say 15 degrees is 45 degrees minus 30 degrees. Okay, let's go with that one. So cosine of 15 degrees is the same thing as cosine of 45 degrees minus 30 degrees. And since we've written it this way, we can use the cosine, cosine, sine, sine identities. So this is going to be cosine of the first angle, cosine of the second angle, cosine, cosine, and then it's going to be the opposite operation, so from a minus to a plus, and then sine, sine, first angle, second angle. So we have 4 ingredients to work out, and we know how to do each one of those because 30 degrees and 45 degrees are special angles. Okay, so at this point in the game, you could look them up on a triangle or look them up on the unit circle, whatever you want. I'm not going to write all those steps anymore. I'm going to assume that we can just do this. So cosine of 45 degrees, one way or another, we know that's root 2 over 2. Cosine of 30 degrees, we know that's root 3 over 2. Sine of 45 degrees, root 2 over 2. And sine of 30 degrees, 1/2. So what we get is rad 2 times rad 3, that's rad 6. This is all over 4. Plus rad 2 times 1 is rad 2, all over 4. And we have a common denominator, so we can just say this is rad 6 plus rad 2 over 4. And that is the exact value of cosine of 15 degrees. And we got it using the sum and difference identity for cosine. Okay, this works perfectly well in radian measure 2, of course. Why wouldn't it? And the process would be pretty much the same. In fact, it's exactly the same. We have this unfamiliar angle, so we need to find a way to write it as a sum or difference of two familiar angles, of course in radians. So yeah, well that's not so straightforward when it's hard to visualize the fractions involved here. So a trick that I use is just focus on the numerator and say, well, what can we do to make 17? Well, how about 16 plus 1? So 16 over 12 pi times 1 pi over 12. And are those both angles that are special angles that we love? Well, 16 pi over 12 reduces to 4 pi over 3. So that's a good guy. We know how to deal with that angle. It's on the unit circle. But pi over 12, no, that's not a unit circle special angle, right? It's not a multiple of pi over 6 or pi over 3 or pi over 4. So this breakdown doesn't quite work. Okay, well, what's another way to build 17? How about 15 and 2? So, okay, does this one reduce? Yeah, we'd get 5 pi over 4, right? By dividing everything by 3. That's an angle we're familiar with. 2 pi over 12, that reduces to pi over 6, and that's also a special angle we're familiar with. So this one works. Okay, it's not at all the only solution. You could have gone with 20 minus 3 to get your 17, and that also would produce two different angles. So there's actually many different ways you can put two angles together to get the weird one that you're interested in. So let's write cosine of 17 pi over 12 as cosine of 5 pi over 4 plus pi over 6, as we just worked out. And now we can use the cosine, cosine, sine, sine identity. So this is cosine, first angle, cosine, second angle. The plus in the middle here will become a minus out here, and it's cosine, cosine, sine, sine. So sine, first angle, sine, second angle. Okay, we have 4 little ingredients to work out, and we know how to do each one. So cosine of 5 pi over 4. 5 pi over 4 is in the third quadrant, so it will be negative rad 2 over 2. Cosine of pi over 6, that's rad 3 over 2. Minus sine of 5 pi over 4. That's also in the third quadrant, negative rad 2 over 2. And sine of pi over 6 is 1/2. So, all right, putting this together, we get negative rad 6 plus rad 2 all over 4. And that is cosine of 17 pi over 12. Notice that this quantity is actually negative because rad 6 is larger than rad 2, so negative rad 6 will be very negative compared to the rad 2, so this whole numerator is negative. And that makes sense because 17 pi over 12 is in the third quadrant. So being in the third quadrant means the cosine value is negative. By the way, if you're really uncomfortable with all this fractional work that we did, especially right at the start, you can just convert this to degrees and do all your work in degrees here. You'd get the same answer, wouldn't you? So that's perfectly all right if you wish to do it that way. Okay, so here we're given some information about a couple of angles, S and T, and we're asked to find the cosine of yet another angle, which is S minus T. So yeah, we have 3 angles in this problem, S, T, and S minus T. We're going to need an identity right here at the beginning, and that is, of course, the sum and difference identity for cosine. So let's note that cosine of S minus T is cosine, cosine, sine, sine, right? So cosine, first angle, cosine, second angle. Of course, we're going to get a plus here. Sine, sine. Okay, so that's what we're after. We're after cosine of S minus T, which means all we have to do is individually find cosine of S, cosine of T, sine of S, and sine of T, and then put them right here and do the arithmetic, and we're going to be done. And in theory, we're halfway through because we have cosine of S. That was given to us. And we have sine of T. That was given to us. So really, we only need to find cosine of T and sine of S. Okay, so let's start by finding cosine of T. Okay, now we're finding cosine of T, and we were given sine of T, and we know that T is in quadrant 4. So for this little sub part of the problem, we actually can just use a triangle. And let's just do that. So we know that the sine of T is negative 24 over 25. Well, on a triangle, we only have positive lengths. So we're going to say this is 24 over 25. And that means that this missing side we'll call b for base. We know that b squared is 25 squared minus 24 squared. And that's a difference of squares. So 25 minus 24 is 1. 25 plus 24 is 49. So this is just 49. And therefore b is equal to the square root of 49, which is 7. Okay, so we can conclude that cosine of t, which will be adjacent over hypotenuse, is 7 over 25. And because t is in the fourth quadrant, and we're taking the cosine, and cosine's positive in the fourth quadrant, we know that this is going to be positive 7 over 25. Okay, so now the other ingredient we needed was sine of s. And we'll use a triangle for that one as well. So we know that cosine of s is 15 over 17. So let's just find this missing side. We'll call a for altitude. So a squared is equal to 17 squared minus 15 squared. Again, using the x squared minus y squared factoring formula, we can see 17 minus 15, which is 2, times 17 plus 15, which is 32. So we get that a squared is 64. And that tells us that a is, of course, square root of that, which is 8. So we can conclude that sine of s is opposite over hypotenuse. So it's going to be 8 over 17, except again, s is in the fourth quadrant. Sine values are negative in the fourth quadrant. So this will be negative 8 over 17. Okay, so we have all 4 of our ingredients now. We can go back to the main thread here and simply plug them in where they belong and do the arithmetic, and we'll have our answer. So cosine of s minus t, which of course is cosine of s, cosine of t, plus sine of s, sine of t, is all of these pieces. So cosine of s, that was given, 15 over 17. And cosine of t, we evaluated, that was 7 over 25. Plus sine of s, which is negative 8 over 17. And sine of t, which was given as negative 24 over 25. Well, 16 quarters is $4, right? So 17 quarters is $4.25. And in the numerator, we have 15 times 7, which is 105, and 8 24s, which is 192. So that would be 105 plus 192 would be 297. And as odd as that fraction is, that's our final answer. All right, let's verify this trigonometric identity. Now, we've been picking up the habit of starting with the more complicated side, right? And one could argue that the right-hand side is more complicated. It's got a thing that's squared, it's got 2 terms, but keep in mind that if we started with the right-hand side, we'd have to find a way to arrive at this cosine of 2x, and it's not obvious how we would do that. On the other hand, cosine of 2x, we have a directive right away we can apply to that. We know that that's cosine of x plus x, and we can use, you guessed it, the sum and difference identity for cosine. So let's start with the left-hand side. Remember, never write down the identity. Always just write down one side and work with that side until you arrive naturally at the other. So cosine of 2x is cosine of x plus x. That's what 2x means. It's x plus x. So this allows us to write cosine, cosine, sine, sine, right? Cosine of the first angle, cosine of the second angle, of course they're both x, minus sine of the first angle, sine of the second angle. So, okay, cosine of x times cosine of x, well, that's cosine squared of x. And sine of x times sine of x, that's sine squared of x. Well, this is sort of familiar. This is kind of like cosine squared plus sine squared, but it's not. It's cosine squared minus sine squared. And what are we trying to get? We're trying to get this form. So we sort of have the cosine squared where we want it, but we don't quite have the 1 yet. However, we can probably use the fact that we know that sine squared of x is indeed itself 1 minus cosine squared. And that's because cosine squared plus sine squared is, of course, 1. So we could write this as cosine squared of x minus the quantity 1 minus cosine squared x. All right, well, if we distribute this negative, we'll get -1 and then plus cosine squared x. And aha, that's going to give us what we want, because if we combine the like terms, the cosine squareds, we'll get 2 cosine squared minus 1. Well, that's the right-hand side. So we win.